Alright, in this video we're going to talk about section 1.1 day 2, and we're going to talk about different uses of radians other than just measuring angles. So recall from the formal definition that we saw in the last video that radians theta is going to be equal to the ratio of S and R, where S was arc length and R was the length of the radius. From this we can actually get a formula for arc length. So if S is the arc length, solving for S, we can say that S equals R theta. And remember that S is arc length. Theta is the angle in radians. So it has to be in radians if this is going to work. And R is the radius. So S is arc length. Theta is the angle in radians, and R is the radius. So S equals R theta. That's how we're going to find the length of an arc for a circle. So let's look at a problem where we can use this. So a circle has a radius of 4 inches. Find the length of the arc intercepted by a central angle of 240 degrees. So we want to use this S equals R theta. So we need to think about R and theta. They were very straightforward. They told us R was 4. But they didn't tell us theta, so they gave us a degree measurement, 240 degrees, but we have to be in radians if this is going to work. So we have to turn 240 degrees into radians. So we have to think degrees to radians is going to be the degrees times pi divided by 180. So filling that in, we're going to get 240 pi over 180. 240 over 180 is going to be 4/3. So we're going to get 4 pi over 3. So theta equals 4 pi over 3 because we have to be in radians. And now we just have to plug R and theta into our formula. So S equals 4 times 4 pi over 3, which is going to be 12 pi over 3. So the length of, I'm sorry, not 12, 16. Oops. 16 pi over 3. So the length of that arc is going to be 16 pi over 3 inches, right? Because our units from the beginning were inches. If you wanted to, you can put that into a calculator, and it's approximately equal to 16.76 inches. Which makes a little bit more sense realistically than 16 pi over 3. But that's how we're going to get our arc length. We can also talk with radians about linear and angular speeds. So a linear speed measures how fast a particle is moving. So how fast the particle is moving. And that particle can be anything. It can be a car, a bug, a person. Anything that's moving is going to be considered that particle. So the formula for linear speed is V equals S over T. Where V is the linear speed, S is the arc length, and T is time. So S is still that arc length we had before, where S equals R theta. So that's where our radians are going to come into this. So V equals S over T is going to be our linear speed. So let's look at a problem where we can use that. The second hand on a clock is 10.2 centimeters long. Find the linear speed of the tip of this second hand as it passes around the face of the clock in centimeters per second. So if we think about our linear speed, remember we have to say it's V equals S over T. So we need to think about what S is. So remember S is R theta. So we know R, second hand of a clock, is 10.2 centimeters long. So if you think about that as the radius of a circle, we know R is going to be 10.2. And if we have to think about how fast it's going around, we can pick how long we want it to be. So it's really easy if we just pick one full rotation. And one full rotation all the way around a circle in radians is 2 pi. So from that we can get that S is equal to 10.2 times 2 pi, which is going to be 20.4 pi. So it's going to travel the arc length of 20.4. Now we get to pick that because we can also pick how much time we're talking about. So when we say V equals S over T, we go to V equals, we found 20.4 pi, but the time that it took us to do that was 60 seconds, or 1 minute. So we're going to keep it in terms of seconds because our problem wants us to be in centimeters per second. So we can keep it like that if you want, 20.4 pi over 60 centimeters per second, or if you want to plug that into a calculator and get a decimal answer that might make a little bit more sense, we get 1.068 centimeters per second. So S over T is going to be our linear speed, S being arc length, T being time. So the other type of speed that we can deal with is going to be angular speed. And angular speed is just how fast the angle is changing. So not necessarily how fast something is moving, but how fast the angle changes. So formula for angular speed is omega, this little W thing, equals theta over T. So it's very similar to linear speed, except we don't want the arc length, we want the angle. And that should make sense because we're talking about angular speed. So the omega is the angular speed, theta is the central angle, and again, that's got to be in radians. And T is still time. So looking at an example of angular speed, a Ferris wheel with a 50-foot radius makes 1.5 revolutions per minute. Find the angular speed of the Ferris wheel in radians per minute. So there's our units, radians per minute. So we know it's going to be omega, that's a weird omega. Omega equals theta over T. We know that T's got to be in minutes, right? Radians per minute. So we're going to look up here and see that we get 1.5 revolutions per minute. So if we think about 1.5 revolutions, so one revolution all the way around has a radian measure of pi. And we're going to go another 2 pi, and then we're going to go halfway around again. That's going to add another pi. So this 1.5 revolutions is really going to have an angle measure of 3 pi. So our omega, can't draw omegas today, the omega is going to be equal to the angle measure, 3 pi, divided by the amount of time it took us to get there, 1 minute. So 3 pi radians per minute is going to be our answer. And the last thing that we can talk about as far as uses for, or other uses for radians, is going to be the area of a sector of a circle. So if you don't remember what a sector of a circle is, if you have the circle, you draw a central angle. The area that you just cut off that way, that's a sector of a circle. So the area of the sector of a circle is going to be A equals 1/2 r squared theta, where r is the radius and theta is the central angle measured in radians. So again, has to be in radians or it's not going to work. So 1/2 r theta times, 1/2 r squared times theta. So looking at a real quick example of that. A sprinkler on a golf course fairway is set to spray water over a distance of 70 feet and rotates through an angle of 120 degrees as shown in the picture. Find the area of the fairway covered by the sprinkler. So if this thing were to go all the way around, this 70 feet right here would serve as the radius. Now the problem again is going to come from the fact, like we saw earlier, that they give us degrees and we need radians. So again, if we're going to think degrees to radians, we're going to do degrees times pi over 180. So we're going to go 120 pi over 180, which is going to simplify to give us 2 pi over 3 radians. So we know 2 pi over 3 is theta. We know r is 70. So a equals 1/2 times 70 squared times 2 pi over 3. So we can do a little simplification here. The 2 in the numerator here and the 2 in our denominator here are going to cancel. So 70 squared is going to be 4,900. So our area is going to be 4,900 pi over 3 feet here, and we're talking about area, so that's going to be square feet. And if you want to throw that in a calculator, to the nearest foot, that's about 5,131 square feet. So that's going to do it for this video. We will see you in the next one.